Hi everyone, I'm Cody Root. This is the Church of Logic, and today I'm going to talk about something I wanted to talk about for a long time, but I actually haven't prepared that well, so bear with me. I'm going to talk about what if the big open conjectures that we hear about if we're interested in mathematics, what if those are undecidable? This is a question that comes up all the time on like math forums and especially by people who've heard about undecidability but don't um, necessarily have this very nuanced understanding of it. The question is okay, we have Riemann hypothesis, we have all these really hard questions, odd perfect numbers, the infinitude of Mersenne primes, the infinitude of, twin primes. What All these are famous conjectures, easy to explain. Um, the 3n+1 conjecture, the what is it called? The hailstone conjecture. That one comes up a lot as well. Uh, we know that these are open. We know these are hard problems, and we know that undecidability is a thing. What if all these conjectures we haven't been able to solve them because they're actually undecidable? All right, I'm gonna try and unpack what this could mean and the likelihood that this is the case given our current understanding of things. So the first thing to observe, I talked last time about the arithmetic, the logical complexity of statements. I said, statements can be kind of stratified into a hierarchy where you have statements about arithmetic and then statements about, that quantify over sets that are higher. The arithmetic ones, again, can be stratified into basically the number of alternating quantifiers that you need when you state the conjectures. The simplest ones at the very bottom, the very simplest ones are the ones that are decidable, which is to say the ones where you only have to look at a finite number of integers to decide whether they're true, right? Like saying there are, four prime numbers less than 7, right? That is a very decidable statement, and you can feel pretty confident that you would know how to solve that conjecture, right? Okay, so those are the simplest ones. They're called the delta zero ones, or, pi zero sometimes. And then the pi ones quantify over a number and then ask a decidable statement um, after those. If you hear squeaking, it's my dog, and I apologize. And okay, so what are examples of conjectures like that? Well, the twin primes conjecture is such a statement, right? Saying that there's infinite number of twin primes is a basically a pi 0 1 statement, right? You're saying that every number has a twin prime above it. Sorry, that's a bad example. I think that's a pi 2 statement. So a clearer example of a pi 1 statement would be, let's see, would be the Catalan conjecture, for example. No, sorry. Let me find a better example. I should definitely have prepared this. The Goldbach conjecture, there it is. The Goldbach conjecture says that every even number is the sum of exactly two primes, right? So for any even number, say, 42, you can find two primes less than 42 that add up to it, all right? This is a for all statement, right? It's saying every number, if it is even, then some property. And that property is decidable because you can look at all the numbers that are prime that add up to it, but you only need to look at the numbers that are smaller than it, right? You're saying there are two prime numbers that add up to it. Those numbers have to be smaller. All right, so this is a pi 0 1 conjecture. And what I said last time was that uh, the the arithmetic statements are stratified by this alternation of quantifier. And in theory, as you go up in the stratifications, you can have harder and harder statements of different levels. But you find undecidable statements at each level, basically. And of course, we know that there are undecidable statements at the first level, at pi 1, because, hey, guess what? The famous undecidable statement, PA is consistent, is already at the pi 1 level. Now, I do mean undecidable by saying, hey, it is neither provable nor refutable in a given sort of reasonable logical system, right? But to say this, you have to specify a logical system, right? So now we're facing a second problem, which is, okay, when you say that these conjectures are undecidable, what system are you talking about? Relative to which system? What's kind of cool is that we can say that there exists undecidable statements with respect to any system. And Gödel already knew this, but it was much easier to prove once Turing had done his work, because um, you can talk about you know the halting problem. You can express things via Turing machines, and then you can say, oh well, if things were decidable, right, then we'd have a Turing machine that decides whether these conjectures are true. And no such Turing machine exists. Therefore, there's no way to decide, these conjectures. And so this notion of Turing machine is very flexible. But for a given problem, right? For a given Turing machine, whether it halts or not, right? As far as classical logicians are concerned, that is either true or it's not true, right? So it doesn't make sense for the truth to be undecided, right? It only makes sense for it to be provable or not provable within a given system. So Turing machines can't really save us here. We have to fix a system if we're going to talk about a specific conjecture. We could say, okay, well, here's a family of problems, and we know that in each family we can find an undecidable problem with respect to any reasonable system of logic. And that's what people did during the years that followed Gödel's original result. We proved that there are some Differential problems, some problems that only involve quantifier-free, equations over the natural numbers that are undecidable in every system, right? But we can only, if you fix a system, you can point to a single Differential problem that is undecidable in that system. And we kind of know that that problem is undecidable, and it involves encoding, right? This encoding of the Gödel incompleteness theorem in this equation. So the equation is horrible. If you look at Fermat's last theorem, it's a very, very simple equation, right? And the question that we're wondering now, and we don't really have an answer to this, is there a natural mathematical problem that doesn't involve talking about Turing machines or piano arithmetic and encoding that in some horrible way into a simple equation that is undecidable, right? And the answer is we don't really have such problems. There are actually, that's not entirely true. There's something called the Hydra problem, which involves writing a number in a certain base, like if you take 7, right, and you write it in base 2, right, that would be 2, let's see, what is 7? 4 plus 3, that would be 2 squared, right, plus 2 plus 2 to the 0, right? And if you change all those 2's into 3's, you get a much bigger number, and then you subtract 1, and then you start over, right? You take it base 3, you change all those 3's into 4's, you subtract 1, right? This thing is going to grow, right? Because you're taking recursive powers of things and you're taking the next number, right? You're replacing all those powers with the next number. But it's pretty easy to prove that that subtracting 1 is eventually going to take over, and this number is eventually going to go back down to 0. All right. People have proven that this is independent of piano arithmetic, which is cool. But the way they've proven it is just so simple and so transparent that it's really not apparent that this undecidability is going to carry over to anything else. A lot of set theorists have proven the independence of these really fascinating problems, like the continuum hypothesis, but the techniques that they've used don't apply to any statements about arithmetic. All statements about arithmetic are completely immune to these undecidability proofs that set theorists use. So all the techniques we have available are just basically not that useful for proving undecidability. And that's something I kind of want to emphasize, which is to say we do not know how to prove undecidability of anything, basically, except the original Gödel statements. There's no real technique. And so for now, proving undecidability of things is just a kind of hopeless task. And honestly, it's not clear that we have any examples, even really known examples, of natural statements which turn out to be undecidable against, say, ZFC, some strong system of logic. We just have zero examples. Now, like I said, maybe that's just because our techniques aren't well adapted for that. But that's also sort of saying, okay, well, this hope we have that all these hard conjectures are just hard because they turn out to be undecidable, that doesn't really solve much because it doesn't give us any avenue for attacking them. We just have no way of showing that these things are undecidable. I also, let's see, I wanted to note something interesting, which is what often happens with these hard number theoretic conjectures is that they first are reduced to a decidable problem. Like Catalan's conjecture, this famous conjecture that says if you take two non-trivial powers, some power of two natural numbers, and you take the difference between them and you get 1, well, that's only possible if one of the numbers is 9 and the other one is 8, right? So 9 is 3 squared and 8 is 2 cubed. And those are the two only non-trivial powers that are apart by 1. All right, what happened in the case of this conjecture is kind of cool. The first thing we did is, solve a bunch of special cases, and then we found this astronomical upper bound, and we proved that above that upper bound there can be no other counterexamples. And then that upper bound was too big to actually check by computer, say. It was really, really, really big. But that did say one thing, which is all of a sudden this conjecture cannot be undecidable in piano arithmetic anymore, because any decidable problem can be solved using the weakest form of arithmetic. And then people worked on it and got that bound down until a number we could check by computer. This was one of the big victories. I think it was proven, in 2002, finally. So, okay, in summary, is it possible for all these conjectures to be undecidable? Yes, it is possible. As of today, until we solve a conjecture, we do not have any good way of excluding the possibility this happens to be a problem which, say, ZFC, some powerful set theory, does not know how to answer. In practice, this has never happened. I gave an example of a problem that's not solvable in piano arithmetic, but that example was kind of somewhat artificially constructed for that purpose, and also it was very easily shown to be both true and also unprovable in PA, right? So ZFC of course solves it. ZFC is much more powerful. And finally, we don't really have any techniques to show that some natural statement is undecidable. We have techniques to talk about logical theories and their decidability. We know how to talk about families of problems using, Turing machines and reducing things to the halting problem. But for a natural statement about arithmetic, we just don't have any way of showing that it's undecidable. We can classify it in the hierarchy of, arithmetic, logical complexity. We can look at how many quantifiers you need, and that can give us an idea. Generally, the lower number of alternating quantifiers are needed, probably the less likely it is to be undecidable. And all the famous conjectures are at the very lowest levels, right? Odd perfect numbers is pi 0, 1. Hey, don't do that. And things like, the Syracuse problem is, pi 0.2 or pi 0.3 at best. So serious mathematicians aren't really considering that possibility too much, but they are kind of thinking about it in the back of their heads. And I guess we'll find out if we see more natural problems being undecidable in the next years. It'd be an interesting development. All right. Until next time, I know I need to go scold my dog. Until next time, please take care.